Hello all, welcome to my YouTube channel. Today we are discussing about a classification algorithm that is logistic regression. So logistic regression, we know supervised machine learning consists of two type of problem, that is classification and regression. So in regression, we need to find a best fit line that fit all over the data. Whereas in classification, we need to find a decision boundary that can correctly classify the data point in corresponding classes. So it's a supervised machine learning algorithm. It belongs to classification. So logistic regression is a probabilistic classifier. It will predict the probability that the new data point belong to each classes, and it will assign the data point to a class based on the highest probability. So it will assign the new data point towards a class that having the probability, the higher probability that the data point belong to that class. So the figure, there are two figures. The first figure represents a linear regression, simply regression, and the second figure is a logistic regression. So linear regression, we are finding a line that is the best fit line that fit all over the data point in the data set. Whereas in logistic regression, we are finding a separation line or decision boundary that can correctly classify all over the point in the dataset to a particular class based on some probability or some conditions. In case of logistic regression, the condition is based on the probability. So, logistic regression is a probabilistic approach to learn a discriminative function, that is a classifier. Mainly, logistic regression can be used for binary classification. It can be used for multinomial classification as well. And in for binary classification, the output can be either 0 or 1. So, in order to convert, so we know the summation of weight and the coefficient, that is the predicted output. In case of linear regression, we have h theta of x is theta transpose x. So in order to convert it into a probability, we are using some activation functions. That's here we are using sigmoid activation function in order to convert the summation of sum of products of coefficients and weights into a probability value that's between 0 and 1. Logistic regression can be binomial, multinomial, or ordinal. Binomial means the output class or the output variable that can have only two specific value, that is either 0 or 1 or yes or no, like that. Multinomial means there are more than two class labels for the output variable, but it cannot be ordered. For example, if we have a data set in which the target can be used to predict either the given figure or given dimensions in the input is for a cat or dog or sheep. So it's a multinomial classification, means there are more than two classes for the output variable, but we can't order uh, like we can't predict or we can't order cat to come first, then dog, then sheep, like that we can't order. So that type of classification is multinomial classification or multinomial logistic regression. And the third one is ordinal. Ordinal is also is a type of multiple is a type of classification or is a type of logistic regression in which the output containing more than two variables or more than two output variable have more than two classes, but it can be ordered, means we can order it as low, medium, high if the output variable is height. So we can order it as low height, high height, medium height, like that. So there are some assumptions for using logistic regression. So we know for a machine learning algorithm, the input data set containing some features. These features are called independent variable. So each these input features that are independent to each other means there is no correlation between these input features. And binary dependent variable means mainly the logistic regression that is used for binary classification. So the output variable can have either two values s or no, 0 or 1, like that. And there should be a linear relationship between independent variable and the logos. Logod is nothing but, so odd is a function or odd is a ratio of probability of an event happening to the probability that it does not happen. Means it refers to probability because probability is the ratio occurrence to total probability. Means p of x divided by 1 minus p of x. P of x means probability that the x event is happen. 1 minus p of x means probability that the x event is not happen, means the complement. Why 1? Because the maximum value of probability is 1. So the ratio p of x divided by 1 minus p of x, that's called odd function. And the logod is logarithm of this odd function is called a logod. So there should be a linear relationship. There should be a linear relationship between the independent variable and the logod. And the data should free from outliers. Then only we can correctly classify the points using logistic regression. And the data should contain a efficient amount of data. These are the assumptions of logistic regression. And there is some terminologies in case of logistic regression. There should be a logistic function. This function that transforms the independent variable into a probability range between 0 and 1, which represents the likelihood that the dependent variable is either 0 or 1. So next thing is the main thing, we need to calculate the logistic function in case of logistic regression. So here the h theta of x is what? It's the predicted output. So it's the sum of product of coefficients to the weight or coefficients to the sum of product of coefficients and the independent variable. So the output h theta of x in case of logistic regression, that should be in the range 0 and 1. So 0 less than or equal to h theta of x less than or equal to 1. H theta of x is theta 0 plus theta 1 x1 plus theta 2 x2, like that. And logistic regression model h theta of x equal to g of theta transpose x. So this theta transpose x is a continuous value. It's not in the range of 0 and 1. In order to convert it into a range of 0 and 1, we are using a sigmoid activation function. The sigmoid activation function have the value 1 by 1 plus e raised to minus x. Sigma of x is 1 by 1 plus e raised to minus x. So h theta of x is h theta is what? Theta transpose x. So in order to convert it into probabilistic range, we are applying sigmoid activation function that should be 1 by 1 plus e raised to minus theta transpose x. So the y should be, this is a graph of sigmoid activation function. Whenever x equal to 0, means sigma of x is 1 by 1 plus e raised to minus x. Whenever x equal to 0, then sigma of x is 1 by 1 plus e raised to minus 0, that is 1 by 1 plus 1 by 1 plus e raised to 0, that is 1 by 1 plus 1, that is 1 by 2.5. So whenever x equal to 0, then g of x should be 0.5. Whenever x greater than 0, then g of x should be lead greater than 0.5, maximum 1. Whenever x should be less than 0, then it will less than 0.5 and maximum minus 1. Sorry, maximum 0. So the logistic function should be in the range of 0 and 1. In order to make the target classes binary value, means two classes 0 and 1, we are applying some threshold 0.5. So when h theta of x, that is the sigmoid of theta transpose x, greater than or equal to 0.5, then we predict that data point to the class 1. When the probability, that is h theta of x less than 0.5, then we predict that the x value belong to the class 0. Next thing is cost function in case of logistic regression. In case of logistic regression, h theta of x is 1 by 1 plus e raised to minus theta transpose x. It's a non-convex optimization. We can't apply gradient descent directly here. Gradient descent can apply only to the convex optimization, convex function. If the loss function is convex curve or convex function, then only we can apply gradient descent in order to optimize the loss function, to minimize the loss function. So we are we are applying MLE method, that is maximum likelihood estimate, in order to in order to find the parameters that can minimize the loss function. So here we are applying MLE method to estimate the parameters in logistic regression function in order to optimize the cost function. Here the loss function, for finding loss function, we are calculating the likelihood function. Likelihood function is pi from I equal to 1 to n p of yi given xi comma theta. Pi means the product term. When y equal to 0, then p of y of 0 given x of 0 comma theta plus not plus into p of y of 1 given x of 1 given theta. So this is our likelihood function. We need to maximize the likelihood function. For that we are applying argmax function. So argmax over theta pi from I equal to 1 to p of I given xi comma theta. That is theta value. We need to maximize this likelihood function in order to find the optimum value of parameters theta. So theta ml equal to argmax over theta log of pi from I equal to 1 to n. We are applying log over the likelihood function in order to convert the products into sum. For easier calculation, the log likelihood function. Maximizing likelihood function is same as that the maximizing log likelihood function. After applying log, we are getting argmax over theta summation over I equal to 1 to log p of yi given xi comma theta. So summation argmax over theta summation I equal to 1. Either yi can be 1 or yi can be 0. When yi equal to 1, then the target would be yi. yi log p of yi equal to 1 given xi theta when yi equal to 0. That means the probability should be 1 minus p of yi. So we can give instead of yi when yi equal to 0, then 1 minus yi p of yi equal to 1 given xi comma theta. This should be the loss function argmax over theta loss. So in case of logistic regression, the loss function is minus summation I equal to 1 to yi log h theta of xi plus 1 minus yi log 1 minus h theta xi. So here log h theta xi should be true when yi equal to 1. When yi equal to 1, this portion 1 minus yi log 1 minus h theta xi should be 0. When yi equal to 0, then yi log h theta xi should be 0. Only this portion should persist. 1 minus yi log 1 minus h theta xi. So we can write the cost for a single instance when I equal to 1, then when y equal to 1, then yi means 1 into log h theta of xi minus, that is minus log h theta of x when y equal to 0 for that instance. Then minus log 1 minus h theta x, that is for y equal to 0 the cost. So we need to minimize this cost function in order to find the optimum value of theta. Then now we are converting the non-convex function to a convex form. Then we can apply gradient descent. This is the cost function in logistic regression. It should be achieved or it should be found by using MLE method. So same as in linear regression, we are applying GD for logistic regression. So here the algorithm is we want to minimize j of theta, that is the cost function with respect to theta. For that we are initializing the parameters theta and repeat until convergence theta j equal to theta j minus alpha into derivative of j of theta with respect to theta j. We are applying some regularization in order to avoid the overfitting or in order to handle the overfitting. The regularization can be lasso regression or ridge regression. So regularization means we are penalizing the loss function by adding some additional terms. In case of lasso, we are penalizing the loss function by adding absolute value of coefficient. In case of logistic regression, in case of ridge regression, we are penalizing the loss function by adding the squared coefficient, squared value of coefficient, sum of squared value of coefficients. So The regularized j of theta is j of theta plus lambda into summation j equal to 1 to d theta j square. That is the sum of squared value of coefficients. Lambda is called a regularization parameter. In our case, j of theta is this thing, that is minus summation I equal to 1 to yi log h theta xi plus 1 minus yi log 1 minus h theta x, and adding the ridge regression penalty. Then applying the gradient descent here. This portion represents the gradient descent. The below portion. Next thing is what are the difference between linear regression and logistic regression. So usually linear regression, that is used for predicting a continuous value, it's a type of regression. Whereas logistic regression, that is used for predicting the categorical value, it's a classification problem. Then in linear regression, we need to find a line that best fit all over the data. Whereas in case of logistic regression, we need to find a line that can correctly classify the point. That means we are finding the decision boundaries. Then we are using mean squared error or least square estimation method to find the linear regression or to estimate the linear regression. In case of logistic regression, we are using maximum likelihood method. Then in case of linear regression, there should be a linear relationship between dependent and the independent variable. But in case of logistic regression, we don't need that requirements. And in linear regression, there may be a collinearity between the independent variable. But in logistic regression, there should be no linearity between the independent variable. That's the assumption. Then how perfectly separable class affect in case of logistic regression. So what is perfectly separable class? Perfectly separable class means we are having a data set in which a 50% data that represent the class 0, 50% data that represent the class 1. So when classes are perfectly separable, the logistic regression does not converge to a finite parameter value. The model keeps increasing the magnitude of weights to push predicted probability to 0 or 1. Means it will increase whenever the data is perfectly separable. The model can't learn data and find the decision boundary, because it will apply the gradient descent and try to increase the value of parameters in order to find the optimal value of parameters. It lead to diverge, not to converge to a finite parameter optimum value. So we need to apply regularization here in order to avoid this type of fitting. This type of fitting is known as overfitting. Rather than fit over the data point, best fit over the data point, we try to find the optimum value by increasing the value of coefficients. So it become overfit. In order to avoid that, we need to apply some regularization methods. Then why we are using log loss over MSE? I already told MSE, that is the mean squared error, that we can apply only for convex function or continuous value. That's the error 1 by 2n summation I from 1 to n predicted minus actual whole square. But in our case, this is a classification problem. So the Loss function is a probabilistic value. So we are applying maximum likelihood estimation, that is the log loss or cross entropy, for the case of logistic regression. Then in case of regularized logistic regression, we need to apply feature scaling for better convergence, and scaling that ensures equal contribution of all features to the regularized term, and it improves the numerical stability and speed up the convergence during optimization. So in order to speed up the convergence, we are scale the parameters to a normal range. So in case of logistic regression, we should have a no correlation between the independent variable. Whenever the Whenever there is a multicollinearity exists between the features, then how can we handle the problem? So whenever we have two features, that is weight in kilogram, weight in pounds. So here both of the features are actually same, but they are available in two different units. So either we can remove one feature or we can combine these two features into a single feature using PCA, like using some dimensionality reduction methods like PCA, principal component analysis, or we can apply some regularization method like L1 and L2. L1 that will be used for feature selection. L2 that is distribute weight across both the features. Then how can we handle imbalanced data in case of logistic regression? Imbalanced data means the data set containing 70% majority class A and 30% data for minority class or class B. So the data is imbalanced whenever if we are training a logistic regression over this data, then the model will predict the new data set to a majority class, that is class A here. So the model become biased toward the majority class. It can't predict even the data actually belong to class B. It will predict only class A. Here the accuracy should be high because it will predict towards class A only. But it actually not correct. So poor recall for the minority class. So in order to handle the imbalance of data, we are using two methods, class weighing and threshold tuning. So class weighing, that has a higher importance towards minority class. We are applying some weights for each class. The WY weight of a class A is now total number of samples in the dataset divided by total number of classes into total number of samples that belong to that class. That is the weight of that particular class. So we are updating the loss function with respect by using the weight of each class. Here the minority class gets larger weight for forcing the model to focus on it. And the second method is threshold tuning. Class weights are used along with our training. We are updating the loss function to make to make more focus towards the minority class. But in case of threshold tuning, which is a post-training method, which is also used for what class imbalance to handle the imbalance in the data set. So in case of logistic regression, we are using sigmoid activation function. Here the default threshold for classifying for predicting the class is 0.5, means if the sigmoid output is greater than or equal to 0.5, we are assigning the data towards a class 1, whereas whenever the probability or whenever the sigmoid activation function value that's less than 0.5, then we are assigning the data point towards the class 0. So this is the default threshold, that is the 0.5. So we are tuning this threshold in order to avoid this class imbalance. Either we can uh, tune the threshold value less than 0.5 or greater than 0.5. That improve the recall is a post training method, so the model remains unchanged. Then, for the case of linear regression, for the case of XGBoost, we have a feature importance. Feature importance that measures which features give more importance towards predicting the target value. So, in case of logistic regression, how can we measure feature importance? Either we can measure by using the magnitude of coefficient. So, we have our loss function. We are applying sigmoid function to sum of product of coefficients and the independent variables. So we can measure the magnitude of coefficient, which feature have high coefficient, then we can identify that that feature has higher importance. For example, beta age. Beta is a parameter coefficient of age feature is 1.2 and beta cholesterol is 0.3. The age has stronger influence, we can say like that. And the second method is odds ratio. Whenever the coefficient beta that is equal to 0.5, then we are calculating e raised to beta. 1 unit increases double the order. E raised to 0.7 equal to 2.01, that means 1 unit on that x, that double the order. So we can calculate the feature importance like this also. And the third method is permutation important. Here we are we are dropping the features randomly and then calculate the evaluation methods like accuracy, precision, recall again, and then we can identify whether the whether the feature is important or not based on changing the value of, or whether the evaluation metric values are dropped or increased. We can or not changed. We can based on that we can identify whether the feature is important or not. And the fourth one is we can use L1 method, that is lasso regression, to remove the or to identify to select the best features. So through this presentation we studied what is logistic regression, what are the different types of logistic regression, the loss function in case of logistic regression, how logistic regression handle the imbalanced data, how logistic regression handle the perfectly separable data, or how logistic regression became a perfectly separable data set. Then difference between the linear regression and logistic regression, and how the logistic regression handle the highly correlated data set. Then what are the different methods for handling the imbalanced data, threshold tuning and classifying, and how can we do the feature importance for the logistic regression model. Thank you all. Thank you for your patience and thank you for watching. We'll see in the next class.